Next up, let's talk about non-lexical lifetimes. This is a feature that was not in the original release of Rust, but has been added over time to the language to help developers. So the concepts from the previous lessons are technically true, but there's an important nuance to point out when it comes to the lifetimes of references. So the word lexical means lasting until the end of the block. The inverse, non-lexical, means the opposite, not lasting until the end of the block. If the borrow checker can validate that there is no use of a reference beyond a certain point in the code, then it treats the end of the reference's lifetime as the last place it is used rather than the end of the actual scope or block. So I recommend using this strategy when you study a reference. Look at the last use of the reference in the code rather than the scope or the block that the reference is within. So let's take a look at two examples. Here I have the code from the previous lesson. We have a string and a string reference assigned to my pet, and here we are outputting that reference. Let's imagine that we have 100 lines of code in between lines 3 and 5. The borrow checker observes that we need to use the my pet reference right here, so the actual lifetime of my pet begins when it is declared and ends at the last point where it is used within the code, where it is relevant, right? Now, let's consider the difference between this example and this one. I'm going to move this line up. So once again, we are taking a reference and then we are printing it, but let's now imagine the 100 lines of code come after the last use of the reference. Technically speaking, the end of the my pet reference's lifetime is here on line 4. This is the entire lifetime of my pet. This is the complete region of code where my pet is alive or valid. And that is because the borrow checker is smart enough to understand that my pet, the reference, is not needed at any point afterwards. And thus, there's no chance of accidentally referencing an invalid value after the last use of my pet right here, because there is no more use of my pet. So I want to actually take you to the Rust proposal, the actual document that was submitted when the Rust development team was entertaining the possibility of making this change, because I want to show you the before and after, what code looked like in Rust before non-lexical lifetimes for references, and then what code is able to look like afterwards. So let's transition now to that document. So here is the original proposal for non-lexical lifetimes in Rust. I'd like us to focus on this example right here. This example was invalid before the introduction of non-lexical lifetimes. And now with the addition of non-lexical lifetimes, it is a valid piece of code that the compiler will allow. So let's take a look at what's happening here. We have a vector called data, and then we are taking a mutable reference to that vector. It's a slice, so slice is the variable here, and it's basically a slice to the complete vector. So basically a slice or a fragment representing the entire original container, and this is a mutable reference. Then that slice reference is being passed into a capitalized function that expects a mutable reference. As we can see here, this is the last use case of the slice mutable reference. So technically, it's not needed at any point after the end of capitalize. Recall that in Rust, we cannot have more than one mutable reference at the same time. We can have any number of immutable references, but only one mutable reference. And that is to prevent the scenario where multiple references try to change the data at the same time and then are working with data that one of them does not expect. It's like two people borrowing something at the same time and trying to change it at the same time. It creates some potential for errors. We can only have one mutable reference at a time. The push method on the vector tries to append an element to the end of the vector. And so the push method depends on a mutable reference to the vector. So the reason this code would not compile is because the slice reference did not have non-lexical scope. The mutable reference of slice, its lifetime lasted until the end of the function, in this case the bar function. That means the push method trying to take a second mutable reference to the data vector was illegitimate, and thus the code would not compile. However, as we can observe, this example is totally safe because there's no actual logical point where there will be two simultaneous mutable references. And that is because the slice reference is not actually used at any point after the call to the capitalized function. It is as good as not being alive, right? So before non-lexical lifetimes, this code would not compile. Now the compiler and the borrow checker understand that the slice reference's lifetime concludes right here. That marks the end of that reference being alive, which allows the push method to take a new mutable reference. And it's still one at a time. This is one mutable reference, then here, then here, then here. But they're all independent of each other, and there's no point where there are two mutable references happening. So that's the problem that non-lexical lifetimes allowed the Rust team to solve, these kinds of inefficiencies. You can see what the previous recommendation was that you create a separate scope. The reason this solution worked is because it forced the slice variable to live within its own scope, its own nested block, which forced it to go out of scope and thus forced its lifetime to end. So at that point, the compiler could understand that the slice reference was done, and thus we could borrow another mutable reference for the push method. We've seen syntax like this throughout this section. This was the solution before the introduction of non-lexical lifetimes. It's kind of weird because we're adding stuff to the code just to bypass this inefficiency. With non-lexical lifetimes, we now can have code like this compile just fine without the need for any extra curly braces. So once again, the lifetime of a reference will end at the last point it is used, not technically at the end of the scope it is within or the block it is within. That's why people say that lifetime and scope are not technically the same thing. They oftentimes are related, but they don't necessarily have to be. And so I want to make that distinction clear with examples like this.